Go through this question in two different ways. The way that I did it was to focus on whether the line is parallel or not, whereas in the second way, I'm going to look at, first of all, whether they intersect. There are going to be crossover between the two methods, though. So the first thing to do is get from Cartesian form to the vector equation of a line. The vector equation is A plus lambda B. Whereas we've got a line, we start from the origin, we get onto the line using A, and we go along some multiple of B to get to our point. For example, here. So that means we could write x, y, z is equal to ax, ay, az plus lambda times bx, by, bz. And we could rearrange this. So lambda is going to equal, if I take the top path, I could do x minus ax divided by bx. That would be a way to get lambda. But I could also get it by doing y minus ay over by, or z minus az over bz. So this shows how we can go between the two. Because now you can see, right, well, I've got my ax, it's just minus 2, for example. So for us, I've got r is going to equal, and I'm basically just taking the negative of each of these top bits, minus 2, 5, 4, plus lambda, and then it's just the b's are going to be 1, minus 1, minus 3. So the other way to do it is just to say, right, this is lambda, and so I'm going to get x is, 1 lambda minus 2, and you can see the same thing comes about. So there's our vector equation. The key thing is that the direction vector is this 1 minus 1 minus 3. So um, if the line is parallel to the plane, then it must be that the normal vector from the plane, let me start talking about that because this is the normal vector. This is in the form r dot n equals a dot n, where r is our general kind of position vector on the plane, n is the normal vector, and then a is like any point that gets us onto the plane, and then n is again the normal vector. Sometimes it's called d on the right, but I like to write it as a dot n to remind me what it is. So for us, n is just this 1 minus 2, 1. And so what we can do is we can take our line and we can dot it with 1 minus 2, 1. We're going to get 1 plus 2 minus 3. We're going to get 0. What that means is that the normal vector and the line are at right angles, which means it's going to be it's going to be parallel or in the plane itself. So therefore, line parallel to plane or in the plane. So I just really now need to investigate a point and see if I get minus 7. So when r equals, and now I would use my, where's it gone? Minus 2, 5, 4. So if that is in the plane, then when I dot it with the normal vector, I should then get minus 7. So I'm going to get, sorry, I'm just checking, is that minus 2? Yes. So I'm going to get minus 2 minus 10 plus 4. This gives minus 8, and that's not equal to minus 7. So I've shown the line is parallel to the plane. I've shown, however, that it's not in the plane itself, and therefore line is simply parallel to the plane. So what I meant originally was that it was parallel but away from the plane, or kind of if it's in the plane, it's still kind of parallel to the plane, but it's like within it, so it's slightly different. Okay, without, actually, don't say without intersecting. Okay, since it's parallel, there's no way it could ever intersect. So that's how I did it. Okay, method two is to focus actually on where it intersects, if indeed it does. So find where line and plane intersect. Now we have x, y, z equals, and I'm just using this up here now, it's going to equal lambda minus 2, then 5 minus lambda, and 4 minus 3 lambda. So therefore, it must be that if we dot this, with the normal vector, we should get minus 7. Again, we can now find, sorry, I don't know why I wrote z there, that should have been a lambda. We can now find the value of lambda where it intersects. If it doesn't intersect, then we'll find some sort of contradiction. So let's do the dot product. We're going to get lambda minus 2 minus 10 plus 2 lambda plus 4 minus 3 lambda equals minus 7. The lambdas actually cancel out. And we're left with minus 8 equals minus 7, which is not possible. So therefore, line and plane do not intersect, and it must therefore be that they're parallel. There's no other scenario that we could have. So two slightly different approaches. Definitely worth thinking about the second one because just for another time you might be asked to actually find where a line and a plane intersect, so that's important. But the method on the left was pretty good as well, I'd say, just showing that they are parallel. I got to say, actually, in hindsight, I think this is slightly better because it just kind of encapsulates everything you need. And if we did need to find the point of intersection, it does it along the way as well. Whereas if I didn't get 0 here, I would then have to use this method over here. So might as well just go with it from the start. But anyway, it's good to talk about both, I think, and go with whichever one you prefer. Well done.